In his studies of deep slab avalanches in Montana, my collaborator, Scott Savage, visited or studied the records of 74 deep slab avalanches. Every avalanche, that is 74 out of 74, had a crust or ice layer as the bed surface. In several ASARC field studies, mostly in the Columbia Mountains of Western Canada, Mike Conlon and Dave Trace found that most deep slab avalanches released on a layer of faceted crystals on a crust. In my studies of dry slab avalanches that surprised experienced avalanche practitioners in Canada, most released on facets or crust or surface hoar. In this video, we're going to focus on faceting above, below, and within crusts, since so many hard to forecast avalanches release on these layers. Where the snowpack is thin, like this, as it often is in a continental snowpack, the temperature gradient is often favorable to faceting throughout the snowpack in early and midwinter. This video focuses on near crust faceting in areas with a deeper snowpack, like this, where extensive faceting is less common. Scott and I have made this video for avalanche practitioners, but we hope recreationists who are interested in avalanche science also find value in it. We're going to assume you are familiar with the basics of faceting, symbols for snow grains, and snowpack instability tests. There are 4 parts to this video. We'll start by looking at 2 ways that facets can form near crusts. First, I'll touch on dry on wet faceting. That is how the facet-crust combination formed that released the avalanche in this photo. Second, we'll look at how facets can form above and below dry crusts, as well as within the soft laminations of crusts. Third, we'll look at how factors such as grain size and rounding affect the persistence of weak layers of facets. In the 4th part of this video, we'll finish with a quiz and some points that may help you anticipate avalanches that release on facets near crusts. Facets on a crust can form as a result of dry snow falling on a wet layer. Part of the wet layer stays at 0 degrees Celsius while the wet layer is freezing. If the snow surface is cooled by a clear sky or cold wind, then the temperature gradient in the dry layer is often favorable to faceting. The facets can form quickly within a matter of hours and often within a day, resulting in facets on a melt-freeze crust. The sequence of rain from a warm front, snow from a cold front, followed by cooling to a clear sky, can cause dry on wet faceting. For our video about the dry on wet process and resulting avalanches, you can search online for Vimeo Facets Crust. Moving on to part 2 of this video. Let's use this slice of a snow profile to talk about how facets can form next to a dry crust. Practitioners usually place thermometers 10 centimeters apart vertically. Traditionally, avalanche courses have used the following guideline. When the temperature difference between the 2 thermometers is more than 1 degree Celsius over 10 centimeters, and this gradient is sustained for a day or more, facets tend to form. However, a temperature gradient of 1 degree per 10 centimeters is not an accurate threshold for faceting, partly because the temperature gradient is a poor proxy for the vapor pressure gradient. Nevertheless, I'll use the traditional temperature gradient threshold to keep this discussion short. Just making up some numbers, let's suppose the average temperature gradient is only half a degree over 10 centimeters, and we somehow know that this gradient is sustained for several days. No facets will form, right? Not so fast. The crust sometimes favors faceting just above and below the crust, even when the average temperature gradient over 10 centimeters is small and not favorable to faceting. In this photo, we see facets have formed above and below the crust, so the temperature gradient adjacent to the crust must have been large enough. Let's look at the effect of the crust on the temperature gradient close to the crust. This graph shows a crust in a dry snow profile. Warmer temperatures are to the right. This red line is the temperature profile proposed by Sam Kolbeck and other researchers. They argued that since the crust was a good conductor, the temperature gradient in the crust would be less than the average temperature gradient over, say, 10 centimeters. That, combined with the fact that the crust is less permeable than adjacent layers meant that there would be a large temperature gradient just above and below the crust. That would explain why we see facets growing above and below crusts when the temperature gradient, averaged over 10 centimeters, is smaller than what is usually accepted for faceting. Nice theory, but do measurements support the theory? Unfortunately, the thermometers that we use are not accurate enough, and the tips of the thermometer are too big to measure the temperature differences over a few millimeters. A couple of decades after Kolbeck's research, separate cold lab experiments by Ethan Green and Kevin Hammonds provided the measurements we needed. Instead of a melt-freeze crust, they used a solid ice lens for their cold lab experiments. I'll show a more recent result from one of Kevin Hammond's experiments. This graph shows a 4 millimeter thick ice lens. The height of the graph is only 1 centimeter. The temperature gradient, averaged over several centimeters, is shown by the dashed line. Somehow, Hammonds managed to place tiny thermocouples just above and below the ice lens. The slope of the solid black line is the temperature gradient that Hammonds measured with microthermocouples. Note the large temperature gradients just above and below the ice lens. Just below the lens, there were 4 microthermocouples placed within 0.8 of a millimeter, which is amazing. The large temperature gradients next to the ice lens have been called supergradients. And yes, Hammonds observed facets forming above and below the ice lens. For more on this study and the important implications for measuring temperature gradients in the field, search for avalanche, review, thermometer, loop. Let's forget about crusts for a moment and look at the temperature profile in the top 30 centimeters of the snowpack. This sequence of 6 profiles over 18 hours is from a study plot well above treeline in Switzerland. Long-wave radiation to the clear sky has caused strong surface cooling, which is evident in several of the profiles. For a video on the energy exchange at the snow surface, search online for Vimeo Heat Transfers Snow. You can see the large temperature gradients in the top few centimeters that can cause near-surface facets to form. The large gradients and reversals extend down at least 15 centimeters into the snowpack. Now, suppose there is a crust about 10 centimeters below the snow surface. As Carl Birkeland has explained, the large gradients combined with the effect of the dry crust will favor faceting above and below the crust. Once deeply buried, the near-crust facets can form a difficult-to-forecast, persistent weak layer. So far, we've been talking about facets that form just above and below a dry crust or ice lens. Here is a laminated crust. The slightly darker grooves are for layers of facets. Facets have formed above the crust, below the crust, and within the softer layer of the laminated crust. This example is from the profile for a fatal slab avalanche. The bed surface was stepped, which showed that in some places the failure occurred in the facets above the crust and in other places within the soft lamination of facets. Other than a brief discussion in this paper, there hasn't been much research on faceting within laminated crusts. I've asked some very experienced colleagues. One said facets are likely to form within laminations if cold, clear weather persists while the laminated crust is within a meter of the surface. Another, who has worked for much of his career in a maritime snow climate, surprised me by saying that facets always form within the soft layers of a laminated crust. Sometimes hard, frozen percolation channels extend vertically down through the soft layers of a laminated crust. These percolation channels are like rebar or bolts and probably make a propagating crack within soft laminations less likely. When I find a laminated crust in a snow profile, I like to slide my bare fingertips along the soft laminations. If I keep hitting an icy channel, I suspect these icy channels increase the fracture resistance within the soft layer. This is probably a favorable indicator that the faceted lamination on the adjacent slope is less likely to release an avalanche. This is a natural dry slab avalanche that released on a faceted lamination within a melt-freeze crust. So while facets above a crust more often release avalanches, faceted laminations occasionally release slab avalanches. Okay, let's summarize near crust faceting wherever the average or overall temperature gradient is small, such as in a maritime or transitional snow climate. This graph shows the increase in grain size over time. Most often, precip particles or decomposed particles above a crust will form rounded grains that are smaller than the original particles. Sometimes, facets will form above the crust within 1 to 3 weeks. These eventually become rounded facets and then rounded grains, although in some winters this might not happen until spring. Now, what is going on below the crust? In my experience, facets often grow faster below the crust than above it. And if the temperature gradient is small, these facets eventually become rounded. When dry snow falls on a wet layer and then the surface of the dry snow is cooled, facets can form within an hour or a day. After the wet layer freezes, these facets can continue to grow slowly before they eventually become rounded. Okay, let's apply faceting above and below crusts to a snowpack instability test. This person is doing an extended column test. I'll add a beefy melt-freeze crust to make a point about crusts in snowpack instability tests, such as the compression test, extended column test, and propagation saw test. Now let's add some facets above and below the crust. Let's suppose that as we are tapping on the shovel, a crack in a layer of facets below the crust initiates and suddenly propagates across the column in the same tap. This is not uncommon because the facets below a crust are often a little bigger and sometimes sharper than the facets above the crust. And let's suppose that, a few taps later, a crack in the facets above the crust initiates and suddenly propagates across the column. For avalanches on a nearby slope with a similar snowpack, which is the bigger concern? The facets below the crust that fractured first, or the facets above the crust? You've got it. The faceted layer above the crust is far more likely to release an avalanche. The early fracture in the facets below the crust, that occurred with fewer taps, is an artificial result of the column being isolated from the snowpack on all sides. To see how common it was for a layer of facets under a crust to release avalanches, Scott and I searched through our records and books on avalanche accidents. We found only a few fatal avalanches that released in facets under melt-freeze crusts, and none of these crusts were thick or knife-hard. So avalanches that release in facets under a thick, hard crust are less common than releases above crusts. Now, in part 3 of this video, let's look at the persistence of near-crust facets. Each point on this graph shows the age of a near-crust facet layer when it released a dry slab avalanche. The age of the facet layers when the avalanche released ranged from about 5 to over 60 days. The facets were mostly 1 to 2.5 millimeters in size. Looking at this point, the facets were 1.5 millimeters in size and the facet layer was about 37 days old when the avalanche released. This graph shows that as the size of the facets increased, there was a weak trend for the age of the facets to increase. Although there are only a few results for rounded facets in this graph, they appear to be as persistent as sharp facets shown by the blue squares. Let's take another look at the age of faceted layer near crusts, this time for compression tests in which the faceted layer fractured. This graph and the previous graph are from this paper about poorly bonded crusts in the Columbia Mountains of Western Canada. The average size of the faceted crystals are along this axis, and the age of the layer when it fractured in the compression tests is along this axis. For each size class of crystals, the sharp facets in blue are plotted separately from the rounded facets. The number near each symbol is for the number of sites at which multiple compression tests on the layer gave consistent results. The bars show the range in age of the facets, specifically the middle 50% of the range. As in the last graph, we see that bigger facets more often fractured in older layers. For layers of sharp facets with an average crystal size of 2 millimeters or larger, we were getting consistent results 2 months after the layer was formed. For these layers of large facets, the sharp facets produced consistent fractures well after the rounded facets did so, which is what we expect. However, for 1 and 1.5 millimeter facets, the layers of sharp facets and rounded facets were fracturing consistently up to 2 to 3 weeks after burial. And there was little difference between the age of the sharp facets and the rounded facets when they fractured in compression tests. These compression test results were obtained from the Columbia Mountains, where many accidents occur in persistent weak layers about 3 weeks old. So there is no difference in the age of sharp or rounded facets in the period when avalanche accidents are common on facet-crust combination. This result, combined with my experience doing fracture line profiles at unexpected avalanches, is why I don't trust rounded facets. Sure, rounding is a trend associated with strength gain, but it doesn't seem to have much effect in the first 3 weeks. But why are layers of bigger facets often weaker than layers of smaller facets? In 1976, Perla and Martinelli proposed that, when sheared, bigger facets on the right would apply more leverage on the bonds than smaller facets on the left. This seems plausible, but the effects of bonding and density should also be considered, which may be why the size of faceted crystals is only weakly correlated with the age of faceted layers when they released slab avalanches. Now let's look at how layers of faceted crystals near crusts that form in early winter differ from the layers that form in the spring. This graph from the Columbia Mountains shows the thickness of layers of near crust facets that released avalanches plotted against the month of the avalanche. Using this point as an example, the avalanche occurred in January in a layer that was 1.5 centimeters thick. Most of the November and December facet layers on crusts are thicker than 1 centimeter. However, most of the March and April facet layers on crusts are less than 1 centimeter thick, often as thin as 1 or 2 faceted crystals. So in the spring, when sun crusts form on sunny slopes, thin, hard-to-find layers of facets may form on the sun crusts. Here is a hypothetical example illustrating the resulting complexity of the spring snowpack. Suppose you dig here and find the storm snow is well bonded to the sun crust down 30 centimeters. Then you get surprised by triggering the storm snow on the sun crust here. A sun crust and the bond to the sun crust can vary insidiously from one slope to the next, and even with small changes in aspect on the same slope. Here is a short quiz to help you retain the key points in this video. Press pause, then read the questions and prepare your answers. Then press play to see our answers. Press pause now. Here are our answers to the quiz. 1. If a wet layer freezes within a day, that is not enough time to result in facets above the frozen crust. This is false, since facets can form above freezing wet layers within 24 hours and sometimes within hours. 2. Thermometers should be placed close to a crust to see if the temperature gradient is large enough for facets to form adjacent to the crust. This is also false. Our thermometers are not accurate enough to measure the temperature gradient close to a crust. 3. Larger facets remain weak longer than smaller facets. This is B, based on a weak correlation. I showed a graph for layers of facets that released slab avalanches. The graph showed an increasing trend with a lot of scatter. 4. Faceted layers above sun crusts are often thin and hard to find in snow profiles. This is true, partly because the facet layers are often very thin, and partly because sun crusts and facets on sun crusts are so variable over terrain. 5. Facets below a crust that initiate and propagate in an instability test is a reliable indicator that the facet layer can be easily triggered by riders on nearby slopes with similar conditions. This is false, since you have cut through the crust to isolate the column for your snowpack tests. The facets below the crust will initiate a crack much more easily than a rider on a nearby slope where the snowpack conditions are similar. Snowpack instability tests are better indicators of triggerability for facets above a crust than below it. Here are a few takeaway points not covered in the quiz. Facets can form above, below, and within a crust, although facets above a crust release more avalanches than facets within or below a crust. In our experience, facets under a thick, hard crust infrequently release avalanches. Rounded facets, we don't trust them. We prefer to be cautious and treat them like a layer of sharp facets. Snowpack instability tests are good indicators of instability, but poor indicators of stability. A single test that indicates stability tells you little about whether you might trigger an avalanche on the slope. This is true for all kinds of weak layers, including near crust facets. Of course, the points in this video about faceted layers near crusts must be interpreted along with other knowledge, information sources, observations, and experience. We are grateful to these folks for sharing their insight on near crust faceting. Scott and I look forward to your comments on the Vimeo site, or you can contact us by email. Thank you for watching this video through to the end.